Well, good afternoon, everybody. I'm Dr. Andrew Bram, an assistant professor at the University of Arkansas. Welcome to today's Pavinar session. Today's topic will be Introduction to Hot Mix Asphalt, or HMA, mix design. Some logistics of Pavinars. If you cannot hear me talking right now, please first check your computer volume and or speakers. And if that doesn't work, you can go to the Illuminate software, which is the webinar software that it's run through. Simply go to the Tools menu, Audio Setup Wizard, and follow the instructions for help. Beyond that, I'm certainly not a computer expert, so I probably wouldn't be of much assistance, but I hope that one of those two solves the problem for you. If you do have a question during the Pavinar, please raise your electronic hand, which if you look on the left side of the screen, there is a list of participants, and underneath that box of participants, there's a little hand with a green arrow pointing upward. And you can simply click on that hand, and that will indicate that you do have a question. After you've clicked on that hand, you can then type a question into the chat box. And the chat box is located underneath the list of participants and the electronic hand. And if you raise the hand, then I know that you are typing something, as that does take a little bit of time. But we'll either pause when the question is raised, or when I come to a convenient breaking point, I will address the question. When you logged into the Pavinar, you entered your email address, and that email address is where I will send your professional development hours certificate, and that will be emailed to you after the presentation. So today we will be talking about an introduction to hot mix asphalt mix design. And we'll kind of cover four general topics. First, there'll be a background, just a real brief overview of the components of hot mix asphalt. And then also, what are some objectives and methods of mix designs in general? And this kind of goes across all different types of mix designs. We'll go over two historical mix design methods, the Hveem mix design and Marshall mix design. And I realize that a couple of these are still used on not only the state level, but especially on city and kind of in the local agencies. So there's still a lot of use for those. But especially at the state and the federal level, those have been replaced by the Superpave mix design. And we'll go over kind of some basic components of that. And then finally, I'll point out some online resources that are available to you. I got a lot of the information in this presentation from a website called Pavement Interactive. It's a very, very nice website with a lot of information about pavements and different topics within pavements. So if you're curious about more details about anything I talk about, there's a good chance you may find it at Pavement Interactive. And also the Federal Highway Administration, or FHWA, has set up an excellent online training seminar for the Superpave mix design. And there's probably 10 to 12 presentations going over all of these details that we'll just brush on today. So this is a very broad overview of each topic, but I think it'll give you just a nice background of mix designs and mix design concepts in general, and then just an idea of different types that have been used currently and also in the past. So to start off with, the components of HMA, or hot mix asphalt, we obviously have a lot of aggregate in there and some asphalt cement to bind it together. But unlike Portland cement concrete, which we covered last month, air is an absolutely critical component of hot mix asphalt. Hot mix asphalt is a so-called flexible pavement, and the air component plays a very large role in that. So breaking down these three components into a little more detail, first you do have aggregates, which are approximately 84 to 93% of HMA's volume, and approximately 93 to 97% mass. As we go through this presentation, you'll see that there are a lot of variables and a lot of components that go into mix design, and those variables and components and decisions dictate the exact volume and mass numbers that you end up with. Overall important characteristics of aggregate can be divided into two general topics, or two general properties, and that would be source properties and consensus properties. Source properties include things like toughness, soundness, deleterious materials, and then the gradation of your aggregate. Whereas consensus properties consist of particle shape, which includes percent crushed faces, flat and elongated, and your angularity, both coarse and fine aggregate angularity, and then also your clay content. Now, you'll note that in general, source properties are things that you really can't change. That depends on where it comes from. Some people do argue that you can change the gradation of aggregates by different crushing techniques and such, but after extracting and crushing, those source properties can't change. Whereas with consensus properties, such as your particle shapes and clay content, it's pretty easy to change kind of in the post-processing. The second component of HMA would be asphalt cement, and that's anywhere between 2 to 6% of the HMA volume and around 4 to 7% of the mass. And this could be a presentation in itself, as could the aggregates be, but talking about important characteristics of asphalt cement, I don't do it justice in one bullet point. But in general, you're looking at things like viscosity, its susceptibility to rutting and permanent deformation, and also its susceptibility to cracking characteristics. And when we get into the Superpave section of this presentation, we'll go over some tests that are able to capture that. But again, asphalt cement is a very broad subject and a very complicated subject. And then finally, the third component of HMA is air, and that's anywhere from 1 to 16% of the volume, depending on the mix type, depending on how dense you compact it in the field, all sorts of variables. And then a question that I always like springing on students is, what would the mass of air be in any mix? And of course it's 0% mass, but that is something that you do need to keep in mind. It takes up a lot of volume, but then when you gain into the details and the nitty-gritty of mix designs, at the end of the day it doesn't have any mass. So that's just something that you have to look out for. And as I mentioned in the previous slide, hot mix asphalt is designed to be a flexible pavement, and the air is critical for this. So changing the amount of air or changing the aggregate structure, the asphalt cement type, these can all contribute toward the flexibility of the pavement. So what is the objective of a mix design? And again, this is regardless of whether it's Marshall, Hveem, or Superpave mix design. But what you want to do is develop an economical blend of aggregates and asphalt that meet design requirements. And that's a pretty broad statement, but at the end of the day, that is what we're doing. We're working with either specifications for the state, specifications for agencies, or we have internal specifications that our companies are trying to provide. You want to meet all of those requirements, and we could do that 100% of the time with no problem if money was not an issue. But of course, at the end of the day, money is very important. So you want to try and balance meeting these design requirements with the economics of it. Some basic key strategies of a mix design, and as you go through the examples of the 3 different mix designs, we'll see more focused areas of this. You want to select and proportion the amount of aggregates, the amount of asphalt cement, and the amount of air that you have in your mixtures. And at the end of the day, you want to prevent pavement deterioration or pavement distresses, such as permanent deformation, fatigue damage, thermal cracking, and moisture damage. So again, these objectives and these strategies are for all types of mix designs. The key steps of a mix design, we'll get into more details on each type of mix design, but they all follow approximately the same steps. You want to have your material selected, both your asphalt cement and your aggregate. The aggregate is important because you can take different sources of aggregates. So if you have 4, 5, 6 stockpiles, they can be crushed rock, they can be river gravel. Recycled asphalt pavement, or RAP, is becoming more and more popular. Now people are even putting shingles in, and that kind of starts putting blurring that line between asphalt, cement, and aggregates. But these different additives you can also put in, which I'm not going to cover in this presentation, but especially the larger aggregates are in charge of designing the aggregate structure. Once you've gotten your materials, you need to batch and mix your asphalt and your aggregates, and then you have to compact them in some way. And you'll see 3 different types of compaction theory in this presentation. And then finally, the last step is to do your volumetric measurements and analysis. And this can include performance testing if you wish, but a lot of things that people look at are terms like air voids, voids in mineral aggregate, or VMA, voids filled with asphalt, or VFA, and effective asphalt content. So when we look at the 3 different mix design methods, we'll kind of see these same key steps repeating for all 3 of them. So what are the mix design methods? I'm going to start with just a real broad overview of the 3 mix design methods, and then we'll kind of go into each one into more details, and you can kind of see some of the steps that are actually involved in the mix design process. The Hveem method was developed in the 1920s, and it was actually developed in California, and it is currently used in a couple of western states. California is still using Hveem. Nevada, I believe, is transitioning to Superpave, but they have very recently used Hveem, and a handful of others are also using it. But again, looking at a state versus a local agency, when you get to these smaller agencies, sometimes you see them using these so-called historical mix design methods, like the Hveem and then the Marshall method. And the Marshall method was developed in the 1930s, and it is currently, as far as I know, not used at any state level. Now, if anyone has more or different information than that, I would appreciate some feedback, but from what I found, that it's not used at any states anymore. But however, it is used in many local agencies, and you'll see when we get into the details of these, a lot of it comes down to cost. And the Hveem and the Marshall methods are relatively inexpensive for equipment and for the actual mix design procedure compared with the Superpave mix design. And that was developed in the 1990s. It uses a lot of concepts that are from the Hveem and Marshall methods, but it also considers traffic and climate. So you have these new parameters being put into the mix design that you have to account for. And it's used in most states now. The majority of states, except for some of those western states, use the Superpave mix design method. However, some local agencies, especially the larger ones, do use it as well. But it is quite expensive. The investment in equipment and the investment in training and technicians and such is a considerable expense. So we kind of covered the general background of material properties, the objectives and strategies of mix designs, and then just a very broad overview of the 3 mix designs that we'll be talking about. But now we'll dig a little deeper into both the Hveem and the Marshall mix design procedure. But before I move on, if anyone has any questions, please raise your electronic hand and I'd be happy to answer them. All right, well, we'll be moving on then. So the Hveem mix design procedure consists of 6 steps, and we covered general mix design procedures, and you'll see a lot of the same concepts that we talked about a couple slides ago. You need to select your aggregate and asphalt binder, and there are multiple ways of doing that. A lot of people have similar sources. A lot of companies use similar sources, or if you're importing a new source, you can play around and see if you get a better performing, maybe more economical mix. You need to prepare your samples, and then you determine the stability. And the stability is actually shown on the left. And that's essentially where a load is applied on the top and bottom of the sample, and then the sample will get pushed down, and as you're pushing down, it will actually expand to the sides. And there's a rubber membrane surrounding the sample, and you can record the pressure off that, and that's called the Hveem stability. Then you go through your density and void calculations. You're often when you're doing your mix design, you use multiple different asphalt cement contents or asphalt binder contents. So you have to go through your density and void calculations for each one, and at the end of the day you need to select your optimal asphalt binder content. So when you're looking at both your aggregate and your asphalt selection, Hveem did not develop an aggregate evaluation selection procedure. So as you go through the mix design, that was something that was not actually a part of the formal mix design procedures. However, over time, they did start incorporating some tests and some properties that they felt were important enough to incorporate into use. So you have your toughness and abrasion, your durability and soundness, cleanliness, particle shape, and surface textures. So these are physical properties, kind of a blend of those consensus and source properties that we already saw. But these are now currently used in order to determine which aggregates you'll use and how you evaluate them. You also have some descriptive properties, such as your gradations, your specific gravity, and your absorption. So these are tests that you can run on your aggregate in order to get a little more information about them. And then finally, you perform blending calculations to achieve your gradation. So a lot of people use Microsoft Excel. There's probably software out there that helps you do that, but when you're using different stockpiles of mix with their different gradations, you need to blend those together in some way. So similar to the aggregate selection, Hveem did not develop an asphalt binder evaluation and selection procedure, but a lot of agencies that are currently or have recently used the Hveem have used many different ways to try and quantify your asphalt binder. They've used penetration specifications and penetration tests, the viscosity test, the kinematic viscosity, your aged residue or AR binder grades, or Superpave binder grades. So as we learned more about asphalt cement and its properties, these concepts started getting folded into typical Hveem mix designs, but he didn't come up with one right at the beginning. So when you're preparing your Hveem samples, you create several trial aggregate asphalt binder blends. So you mix together different aggregates, different quantities of aggregates, and then different types of asphalt, different quantities of asphalt. And at the end of the day, you do want to try and estimate an optimal asphalt binder content, because if you have too much asphalt, sometimes you get rutting, sometimes you get bleeding or flushing. A lot of distresses can happen, but if you don't have enough asphalt, and this is the asphalt binder, sometimes you can get raveling or you get excessive cracking, whether it be fatigue or thermal. So there is an optimal asphalt binder content that you're aiming for, and you can then create a range around that optimal asphalt binder content for your trial blends. And for the Hveem method, there are two ways that they estimate the optimal asphalt binder content. The first is experience. So again, if you have a company or an agency that's been using the same aggregates and same asphalt for a while, you can sometimes kind of have a pretty good guess of what the optimal asphalt content will be. But another way to do this, if you have no experience, is using the centrifuge kerosene equivalent, or CKE test. And what this does is it uses a centrifuge and kerosene as your liquid to come up with what's called a CKE equivalent, and that helps you find the coarse aggregate surface capacity, and from that number you can estimate your asphalt content. So if you go to Pavement Interactive, I think it's .org, but the website Pavement Interactive, you can simply Google that phrase. They actually go through a pretty detailed list of how to run this CKE test, what numbers you get, and the process you go through. But for the sake of this presentation, this is more of a broad coverage, so I won't go into those details. Once you have your aggregate and asphalt content, you compact with the California kneading compactor. This produces a 4-inch diameter samples that are 2.5 inches in height. It's a tamper foot mechanism that is used at 350 to 500 psi. That's the pressure that's used, and it's generally 150 blows. So this is the Hveem method of creating your samples. Then there's a couple of tests to see how the samples perform. The first one I mentioned is the Hveem Stabilometer, and this had a little diagram a couple slides ago. To the right is a picture of the stabilometer itself. And what you do is you measure lateral pressure after applying a vertical load. So you push down on the top and the bottom and see how much the sample expands outward, and you can hook that to a pressure gauge to record how much pressure is being put on the sample in that outward or lateral direction. Another test is a Hveem Cohesiometer, and there's a picture of that on the bottom, and this measures the cohesive strength of a sample. And if you look to the left of that picture, you can see kind of a little brownish metal area. And I'm going to try and draw on the picture here. I've never done this before. But if you look at this place I'm circling here, the sample goes inside that, and it's actually split down here in the middle, so along this dotted line I'm putting in. The sample is on one set of steel plates on the right side, one set on the left side, but it can actually rotate. And you fill a bucket over at the end of this lever with material, and that essentially causes the lever to try and move down, and you split the sample along the dotted line. And you can imagine that is a cohesive failure, because as you're trying to pull that sample apart, you are ripping the aggregate and asphalt cement apart and trying to measure the cohesiveness of the sample. Once you run the stabilometer and cohesiometer tests, you can also find the density and voids from each one of your samples in the trial mix design. And then here's kind of a very typical way to see the Hveem process, and it's basically a pyramid structure, and you start at the bottom of the pyramid and move upward. And this is how you find the optimal asphalt cement using the Hveem mix design. So at the bottom you have this range of asphalt cement contents, and for this example they used 4% asphalt cement, 4.5%, 5%, 5.5%, and 6%. And just from making samples you can tell if there's any flushing that's occurring. So you know, with a little bit of experience, people would say, wow, with 6% asphalt there's too much flushing, this would never work in the field. So you can eliminate that from future testing. Then after you eliminate some, you then run the stability and cohesiometer, and if you pass or don't pass, you can eliminate some more. And then finally you are looking for, the last step is the highest asphalt cement content with greater than or equal to 4% air voids, and that should get you at your optimal binder content. Now, especially with materials that you're not familiar with, this will be an iterative process. I doubt very heavily that you'd be able to get a nice pyramid like this that would go upward in this fashion. But again, there is some trial and error, and you may have to go through the process again, but at the end of the day you're looking for that optimal binder content. Now for the Marshall mix design procedure, we'll see these 6 steps again. It's very similar. You start with your aggregate and binder selection, you prepare your samples, and then you have a stability determination and a flow test. So we're no longer using the stabilometer and cohesiometer, we're instead using your stability and flow numbers. You calculate your density and void calculations, and then finally you pick your optimal asphalt binder content. So we can actually knock number 1 and number 2 off right away, because similar to Hveem, Marshall does not have common aggregate and asphalt binder tests. But if you go back to the aggregate and asphalt binder tests that I listed under the Hveem mix design, a lot of agencies and companies have adopted those and now use them with their Marshall mix design to help them understand and quantify the materials we're looking at. So the aggregate and asphalt binder selection, nothing was officially established by Marshall, but agencies and companies have been kind of fitting more current and more recent tests into their design. So we're going to actually skip right to number 3, the sample preparation. So similar to the Hveem, you create several trial aggregate and asphalt binder blends. You first estimate the optimal asphalt content, and then you compact at -1%, minus 0.5%, plus 0.5%, and plus 1% of that estimate. So you have 5 different asphalt contents, and you make samples for each one of those, and you make the samples using a Marshall hammer. The picture on the left is actually a Marshall mold, and that is 4 inches in diameter, and the final height is only 2.5 inches, which actually sits in that bottom half of the mold on the left. It is a tamper foot, and it has an 18-inch free fall of a hammer with a 10-pound weight. And I apologize for that mistake on the slide. It's 10 pounds, lb, weight. So they have a machine that literally has these hammers that fall 18 inches, and the hammers are 10 pounds, and they hit the tamper foot for either 35, 50, or 75 blows. And you actually go to those blow levels, 35, 50, or 75 blows, and then you flip the sample and do it a second time. And the blow number depends on the traffic level that you have. Here's a small picture of your Marshall stability test. So there's a load frame, and you have 2 metal platens, one that fits on top of the sample and one that fits on bottom, and you push down on that sample at a loading rate of 2 inches per minute. And then in the lower right-hand corner, you measure the stability, which in this graph is in kilograms, and I apologize, it's a little blurry. And then on the other axes, you have your bitumen content, or your asphalt binder, or asphalt cement content. So you run this test and you get some sort of peak load, and that is the stability. So the stability is simply recording what is the peak load during this test. So it increases, and then at some value it starts decreasing again. And actually it looks a lot like the curve that you see there. However, that is not a Marshall stability curve. That is a Marshall mixed design plot that has different levels of asphalt cement, and you can see what the maximum stability is at each one of those levels. So the stability is one measure, and the second measure is your Marshall flow. So you not only are recording the load, but you're also recording the horizontal deformation with the dial gauge, and that measures the plastic flow of the specimen. And flow values are recorded at 1/100th of an inch increments, and your flow value is recorded at the same time as your maximum load. So when you reach your maximum load, you not only have the load, which is the maximum, but you also have the flow value, which is the deformation at that point. And now here's a real nice busy slide, but it has a lot of good information on it. So we're going to start in the upper left-hand corner. So we have a graph that plots your percent air voids versus your percent asphalt binder by weight. And what you do is we're aiming for 4% air voids. So if you go from 4% air voids and then move to the right on that curve, you hit your curve and then go down. And this value, where it intersects, is the theoretical optimal asphalt binder content. And once you have that theoretical asphalt binder content, you can then plot on each one of these other curves, which is the density curve, the flow curve, the Marshall stability, the voids filled with asphalt, and the voids in mineral aggregate, and you simply go up from the asphalt binder over to the intersection of your plot, and then you can record the density as well. So the first graph is going from the y-axis to the curve down to the x-axis, the air voids graph, but the 5 other graphs are actually going from the x-axis, the percent asphalt binder by weight, up to the curve and then over to the y-axis. And you can get your density, your flow, your Marshall stability, your VFA and VMA. And then what you can do is you can compact one last additional sample at the optimal asphalt content and verify that you get the proper density, the proper flow, and the proper stability, and so on. So that kind of covers the historical methods, the Hveem and Marshall methods of mixed design. And again, I went over those very quickly. It is a very broad overview. We could spend a lot more time on each one of those. But if there are any questions, I'll take those now. Okay, so we'll be moving on to the Superpave mixed design, which is most currently used now at the state level and the federal level. So you can see here a lot of similar procedures using the Superpave method, as you saw with the Hveem and the Marshall method. You first gain your materials, your aggregate and your asphalt binder. You prepare your samples. However, now you can also run some performance tests to see how they theoretically will perform in the field. And a big part of the Superpave mixed design procedure is performance tests to try and quantify how they will react to rutting and cracking in the field. Of course, the density and void calculations help you find your optimal asphalt binder content. And then we also have an extra step of your moisture susceptibility evaluation. And that's a picture on the left of AASHTO T283, which is the mechanism used to try and quantify your moisture susceptibility. But we'll go over that in more detail as we go through the mixed design procedure. So first you need to select your aggregate, and the Superpave mixed design procedure went into a lot more detail into this. First of all, they do have a lot of control points. So there's minimums and maximum values for percent passing on each sieve size. So you often go from either a 9.5 millimeter, 12.5 millimeter, 19 millimeter nominal maximum aggregate size. So you have sieves at those sizes as well, all the way down to a P200 aggregate. And at each sieve size, or P200 sieve, excuse me, at each sieve size you do establish, you can establish control points, and there are 4 used for Superpave right now on specific sieves. But if you want more restrictions, you can add control points as you desire. You're looking at both consensus requirements and source requirements. So Superpave does have very specific requirements for your coarse and fine aggregate angularity, your flat and elongated percentages, and your clay content, your LA abrasion, soundness, and also your water absorption. So unlike Hveem and Marshall, Superpave has numbers that you need to meet for your aggregate. And the same with your asphalt binder selection. So I mentioned at the beginning of the presentation that the Superpave system did start incorporating the temperatures into the pavement design. And this is where it comes in, is selecting your performance grade. You can either look at your pavement temperature, your air temperature, or the geographic area you're in order to determine the performance grade that you use. And you want to verify your binder properties to make sure that you're actually getting what you need using the rotational viscometer, or the RV, the dynamic shear rheometer, or DSR, the bending beam rheometer, or BBR, and then the direct tension tester, or DTT. So again, this slide I could easily spend an entire 50 minutes talking about, but this is just a real brief overview of the tests that are required and the concepts that are required for the Superpave mixed design procedure. When you are preparing your Superpave samples, you first create several trial aggregate asphalt blends. Then you estimate the asphalt content. You estimate the asphalt content based on aggregate properties. So using specific gravities, effective gravities, those type of concepts, you can estimate your optimal asphalt content. And then usually you compact at negative 0.5, positive 0.5, and then 1% of that estimate. And you compact using the Superpave gyratory compactor, and you can see a very typical pine compactor on the left. It's on the older side, but it's our workhorse here at the University of Arkansas. And you get a 6-inch diameter sample, and you generally get about 4.5 inches in height. Now you can vary that height depending on what you want to do with the sample. The compactor has plates on the inside, so your diameter is actually a little less than 6 inches. It's 5.89 inches. that you're actually compacting, and that gives you an area of 27 square inches. The compaction pressure is 600 kilopascals or 87 psi, and you can vary the number of gyrations based on traffic level or other parameters that you may be interested in, but that's one way that the number of gyrations can vary. So you put your sample and the mold into a gyratory compactor, then the gyratory compactor actually tilts to approximately 1.25 degrees, and then it rotates at 30 revolutions per minute, and you compact your sample this way. And it was believed that this is more representative of a compactor in the field. So when you think about a steel wheel compactor, that generally kind of pushes the material down. It does not hammer it down like the Marshall, or it doesn't tap it down like the Hveem. It's trying to be more representative of field compaction. Now, of course, as researchers, we like debating just how representative it is, and there's been arguments that actually this circular motion isn't representative of the compaction in the field. But at this point, it's pretty much the best that we have, so it's what we're using now. So some performance tests that were developed in the Superpave system, we'll start with those. You have the Superpave shear tester. Now this is a very interesting test, and it gives you a lot of information about permanent deformation and fatigue cracking. Unfortunately, it's also extremely expensive, and it's extremely difficult to run. You need to glue specimens to steel platens, and you put those platens in a machine, and it actually takes a mixture and applies shearing and tensile loads to it, a whole bunch of different things depending on what you want to do. But unfortunately, the machine is just very expensive, so it actually never really caught on. So you have to dig pretty deep to find out more information about the Superpave shear tester and what it can do. On the other hand, the picture on the right shows the indirect tensile tester, and that's actually a little more user-friendly, and you can get low temperature cracking properties and creep properties out of that as well. So there are some performance tests that are a little more common than others, but in general, these are kind of research grade, found in a lot of universities that aren't as common at the state level or in companies. Now something that is common, however, is the moisture susceptibility, which as I measured is AASHTO T283. And what you do here is that is also an indirect tension test, but it's a little different than the performance test. The performance test tends to be at lower temperatures, whereas the moisture susceptibility is run at room temperature. And you take two sets of material, or two sets of samples, one that's been conditioned in water baths and in a vacuum. So it actually takes water and absorbs water into the sample. You can compare that to an unconditioned sample. And you get two different values of tensile strength, and you want that ratio, the conditioned over the underconditioned, to be a minimum of 80%. And what this is telling us is that your mix is not moisture susceptible. So when it rains, or if there's water pooling a little bit in your mix during very heavy rains, or you have a small drainage problem, the moisture won't cause severe distresses to the pavement. Also at this time, you're looking at different asphalt and aggregate levels, so you have your density and voids calculated. And this is very similar to the Marshall mix design. You start with your air voids versus asphalt binder, so in the upper left-hand corner, and you are again targeting 4% air voids. And you go along that 4% line to the right until you hit the curve. And then at the curve you go down, and you can find your estimated optimal asphalt content there. And for the VMA, the VFA, and your density, you go the opposite direction. So for your VMA in the upper right-hand corner, you start at the 5.5% or so that you found with the air voids, and you move upward to your curve. And you want a minimum of 14% VMA in this example, and that does change with your easel level and some other parameters, but there are established limits for both your VMA and your VFA. So if you guys are interested in like how these limits are for different mixtures and different situations, we can definitely go into that in a later Pavinar. So we've gone over a real broad overview of concepts of mixed design, the Hveem and Marshall mixed design methods, and now the Superpave methods. And I'm going to finish up just with some real basic or real useful online things that you can take a look at if you're looking for more information into this. But if there are any questions, I'll take them at this time. So there are no questions. Going on to the last topic here, here are some online resources. If you go to pavementinteractive.org, or you can simply Google Pavement Interactive, and it'll be the first thing that pops up. Again, this is a very, very nice website. You can simply type in Hveem Mixed Design into their search function. You can find out a lot of information. If you're interested in like asphalt cement tests, like the bending beam rheometer, the BBR, you can type that in and learn a whole lot about that. The URLs do not work on your screen right now, but I will download this as a PDF onto the Pavinar website, and the URLs on that PDF do work. Another thing you can look up is the Federal Highway Administration at fhwa.dot.gov/asphalt tech, ASPH tech. They have put online hot mix asphalt for the undergraduate. So this includes the Superpave mixed design system, but it has PDFs for an introduction, your design and construction of hot mix asphalt, and then you can go down into aggregate properties, asphalt cement properties, the mixed design process. It goes into a lot more detail than what I went into, but all of these are available free for download on FHWA's website. So that's a really good tool if you're interested in extracting some more information out of there. So I'm going to first go over some logistics, and then I'll go over the summary, and if people have questions, you can feel free to stay on. So as I mentioned, I will email you professional development hours to the email address you put in when you were logging on. You can re-watch these Pavinars through the website. You can either re-watch the Illuminate Live session, so you'll actually be able to hear the discussion that goes on while the slides are gone through, or you can simply download a PDF of the presentation as well, and that way you can get to those links and check some details if you want a little more information. Now, please, if you do have topic suggestions, submit them via the website. These Pavinars are for you guys, the state agencies and the contractors, and I would like to know what you guys are interested in and what information that you want. So feel free to submit topics during the on the website, and you'll probably see them next fall or next spring as I plan out the upcoming series. And our next Pavinar will be Tuesday, October 10th, and it will be on white topping, which is a relatively popular, or becoming more popular method of pavement maintenance, where you actually put a thin layer of Portland cement concrete over either Portland cement concrete or asphalt concrete. And it's been around for a while, the technology, but it seems to have been garnering more interest lately. So that will be on Tuesday, April 10th. So in summary, just a real broad overview of your HMA mixed designs, the background, the objectives, and the procedures going in, and getting a little more information about your Hveem and Marshall mixed designs, in addition to the Superpave mixed designs, and then also some online resources. So I would be happy to stick around for as long as you need, but if you have any questions, please feel free to raise your hand and type them into the box. And if not, I hope to see you in April. Thank you all for attending. All right, so Alex has a question. Thank you, Alex. So Alex had an excellent question about the mechanistic empirical HMA design that will allow you to reach an optimal design faster. And Alex, I think this is a really good point. I kind of stuck with lab mixed design procedures. You know, we actually have to go in and make these blends and everything, but I think that as we become more familiar with materials, as we become more comfortable with those materials, and as we're able to translate those base material properties, the aggregate and the asphalt cement, is you're able to translate those into either performance characteristics or characteristics better predicting what will happen during the mix design. I think that we will be able to use computers and computer programs in the future. And you say mechanistic empirical HMA design, and this is kind of a hot term right now because of the mechanistic empirical design guide. Now the mechanistic empirical design guide is looking at pavement structures. And the important thing about that is as loads go over the top of your pavement, there are stresses and strains throughout your pavement layers. And that's the mechanistic empirical portion of it. And when we're talking about mixed designs, I'm not sure how much you can use necessarily stresses and strains. Now I think it would be possible to perhaps simulate, say, a Superpave gyratory compactor or a Marshall compactor or a Hveem compactor. I think that would be possible, and you might be able to extract some of those stresses and strains, which gets you to the mechanistic side. But I think that if you're looking at the concept of mixed designs, I would not be surprised if we see more computer-related mixed designs and the ability to use computers in order to try and optimize our design strategy. So that was kind of a longer explanation than you may have been looking for. But if you have a follow-up question, or if anyone else, oh, thank you, Alex. But if anyone else has any questions, I'd be happy to entertain them. Okay, well, thank you very much for attending. I encourage you all to come to the next Pavinar, which is on April 10th. And also, please feel free to forward this on to other people you may know, whether it's in your agency or within your company, because quite honestly, I don't care if there's 14 people, if there's 30 people, or if there's 100 people. This tool is for the asphalt and the pavement community to use. So I encourage you to spread the word. Thank you all very much, and have a great day.